All right. All right. Yeah, the lesson you be able to describe what power is, how it relates to current, voltage, and resistance, and to calculate an electric bill. All right. So, tell your neighbor what you think. So, plugging this into an outlet, 120 volts. Here's 40-watt light bulb. Okay. 60 watts. And 100-watt light bulb. Okay.
I can actually look at the 40-watt light bulb without
Okay. So, we'll get to the fourth one later. So, correct answer is B, 100-watt light bulb. Right. Okay. There's more power. Okay, so, let's talk about power. So, last semester, we said power is equal to work over time, the rate at which work is done. Okay? Now we're changing that, modifying that a little bit, and saying power. Do you remember how work and energy are related? Like work is the change in energy, and that could be different types of energy. Okay? So this is the change in energy over time. This is the rate at which energy is converted to another type of energy. But both have units. What's the unit for work? Nope. Good guess. What's the unit for energy? Joules. Work and energy are both in joules over time in seconds. This is equal to a watt. Joules per second is equal to a watt. Right with that? Okay. Now, how is that related to this? You might ask. Or maybe you don't ask for it. Okay. What is the unit of current? Good answer. And what is the second. And volt comes from a joule per coulomb. Hey, I see something that looks a lot like this. Okay. Conceptually, here's how this works. Voltage is looking at how much energy each electron contributes. Like the light bulb comes up like, here's what I've got. Okay. And the next electron comes like, here's what I've got. Okay. So, and then what current is how many electrons are going by that certain light bulb every second. So it's like, here you go, here you go, here you go. And multiply those two. What you can find is how much energy is being converted to heat into light per second. Watts. That is why a 100-watt light bulb is brighter, because it's converting electric potential energy to heat and light faster than the 40-watt or 60-watt. Remember that? Okay. Have a conversation. Correct answer is B. Here's how this works. We're going to substitute in for voltage. So that's substitute in there. Power is equal to current times current times resistance. Remember that. Okay. Should do the same trick for the next question, but this time we're getting rid of current. So, yes. Correct answer is A. So we're going to rearrange this to equal current. Okay. So we're going to put that in for current. We have voltage over resistance times voltage equation. But I will give you this equation and this equation. This one, and this one are shortcuts for this and this. Okay. It can be useful, but it's not necessary. Look, you're good. Okay. See? Okay. If this stays the same and resistance goes down, then this is going to make that go up. Inversely related. Okay. And if this is staying the same, this goes up, this also goes up. Directly related. Correct answer is correct answer is B. Both will go positive, go up, but because current is squared, it has more influence. That change is going to be more influential on what happens to power. You get that? Okay. Big picture. Here's some of the skills that I want you to walk away from this class. At the end of the year, be able to look at an equation and like have a just intuitive feel. Like, here's what happens when this happens. They're like, hey, when this increases, that increases, and how to like do some simple rearranging of stuff like these. This is skills that I want you to walk away from with this class. And combining equations, and then also just having an intuitive feel. When you come across an equation in literature on a video, you're like, have just a quick feel for what that means as the variables change without numbers. Tell your neighbor about this lesson. Okay. Correct answer is. Okay. I'm gonna take this. I'm gonna take it through it both like the long way, the tried and true, and then the shortcut. Both are equally valid. So I'm gonna start with Ohm's law. Okay. What variable is staying the same? Not current. Voltage. Why is the voltage staying the same? What determines the voltage? The battery. The battery determines the voltage. Okay? The total voltage is determined by the battery. So that value is fixed. That is a really important point. When you know that one of your measurements is staying constant through the experiment, that's a good anchor point. Okay? So the resistance is increased, therefore causing the current to do what? Decrease. Got that? Okay. And then we go to power. The voltage is staying the same. Current we would reduce that decrease, and therefore power does what? Decrease. Okay. The answer is B. Here would be the shortcut. I would pick this equation because it relates the measurement that's not changing to the measurement that I'm asked that is specifically changing. Okay, so voltage is staying the same, resistance is increasing, power is going to decrease. Correct answer is B. So this is kind of the same question as the previous slide, just going to work it backwards. So power is equal to current times voltage. Voltage is staying the same as we go from bulb 1 to bulb 2. current goes down, this staying the same, resistance has to go up. Bulk 2 has more resistance. Or you can go straight away to this. All right, switching gears a little bit. Calculating your electric bill. This is something that you don't have to worry about now, today, but in a few years, definitely that's going to be on you and your electric bill. So you will see a question like this on the test. You'll see a question like this on the final exam. Okay? So just let you know how to calculate your electric bill. Okay? So what we are doing, calculating the electric bill. We are looking for the amount of energy that we're using. Okay? We have a light that's 60 watt porch light that's left on continually for a month. If you get charged 9 cents per kilowatt hour, how much do you charge for a porch light? So we have 60 watts, that's your power. And now we need time. So we're going to assume that there are 30 days in our month. I need to convert days to what? We need to go to seconds. So there's 24 hours in a day. There are 60 minutes in an hour. There are 60 seconds in a minute. We multiply all that together. Get some really big. Million. 592,000. Seconds. We multiply those 60. We get 155,520,000. What's the unit? Energy. Joules. Okay. One light bulb. You get charged for your electric bill per month. One light bulb. Granted, it was on the whole time, but really, one light bulb. Okay. So you see how this is like a really big number. So the electric companies were like, you know what? We should come up with a different unit because this is like measuring from here to California in inches. It's not wrong. It's just absurd. Okay. So the mile unit that they came up with is called the kilowatt hour. Kind of has the same flavor. Remember we're talking about amp hour yesterday? Kind of has that same flavor. So we're going to be using the same equation, but we are going to be converting your power to kilowatts. So divide by 1,000. So 0.06 kilowatts is equal to, what do you think we're going to convert our time to? Hours. Okay, so that is 30 times 24 is 720 hours. Okay. When we multiply these two, we get 43.3 kilowatt times hour. That's the unit of energy. Which is way more user friendly than 155 million. Okay. Then we figure out how much money that is. It's 43.2 kilowatt hours. And you do 9 cents for 1 kilowatt hour. We find that to be $3.89. So yeah, we do that. This will be on the test and on the final answer. Okay, so you might be like, seriously, $3.89? That's like $3. Like, it's hard to not make turn off the lights. Well, that's fine. You think like you're not. Like, you have your own house, go ahead and leave lights. But also recognize you're wasting money and natural resources like that. There's I would say with LEDs now, way less. I'd say 50 cents.
Plus, take out time for night time.
Yeah, no, I'm saying 50 cents. 50 cents. But that's just light bulbs. Those aren't the main users of electricity. Yeah. Go to your neighbor. Okay, correct answer is we're being a consumer of energy. They're providing energy. This is the rate at which that energy comes to our, like how quickly we're using that energy. But this is how much energy we're using. That's what we're charged. Good with that. Okay. So lastly, what I want to talk about, these light bulbs here, old school incandescent light bulbs. Okay. They are filled with some inert gas, something that's not flammable. Like they take away the oxygen. If you've ever broken one of these, it sounds weird. It sounds like it's pressurized, like it's a weird sound. That's because these are filled with a different type of gas, preventing the filament from burning. If you took this off and tried to turn it on, it just vaporizes. This is an LED light. Okay? I can take this off just fine. It looks pretty, but it works. Okay? So I would assume that more modern houses are being built that don't have these receptacles. They just have LED lights that are, yeah, so they just have LEDs. But so this, turn it on. Okay. Now, I'm going to come around and I'm going to show you those yellow orange things that are LEDs. So the crazy thing is, the wattage on these are like 6 or something like that. But that does not correspond to how bright it is. So, like, for my generation, I know 60-watt light bulb, how bright a 60-watt light bulb is. I don't have really a feel for how bright a 6-watt light bulb is. So what they're doing is they're changing over the limit, which is actually better to tell you how much light is actually produced rather than how quickly energy is being converted. And so if we, okay, I'm going to turn this on, it's going to be bright, so I have to squint, but you can see the dots. Maybe you're going to have to squint to see the dots, the ring. Maybe. Okay, so video here to tell them about LED. Actually, pretty good.
One of the most common ways to generate light nowadays is by using a light emitting diode, or LED. Like the rest of the diodes, as we saw in the previous video, one of its characteristics is that it only allows the passage of electric current in one direction. But we didn't talk about why they emit light, so in this video we will see how an LED works. LED lights have several features that make them one of the preferred options to illuminate, such as having low energy consumption, greater impact resistance, and a longer lifespan, and because of this they are available in many different formats. But instead of going directly to analyze an LED, we will start reviewing how a common diode works, because in theory these can also emit light. It's just that they do it in an inefficient way. If we have a circuit with a lamp and a power source, energy will pass freely. This is because the electrons can move freely between metal atoms, and when connected to the power source, they are forced to move. You know, when you say they move like electrons, but it's just energy. By adding a diode to the circuit, and depending on its position, the current can pass freely or be stopped. And the reason why this happens is because of its composition. Inside the diode, there is a semiconductor material such as silicon. More specifically, two types of this material. If we took a piece of pure silicon and saw its atomic structure, we will find that each atom has 4 valence electrons, which are shared with the other 4.
Okay, just a quick little time out, a little blurb here. Yesterday's activity period was a little subpar. Here's the motivation for why they did that. There is a semiconductor plant coming into West Lafayette in the next 4 to 5 years. They're going to be selling like semiconductor stuff. Okay? If you're interested in sticking around the area and having a good paying job, that is a very, like, it's kind of going to be on a scale of CAT or SIA in terms of the number of employees. Does that make sense? So if you're interested at all in like electronics, like if this is like, oh, that's kind of cool, like that would be a very viable, employable job field. What should I major in? For that specifically, WET, Electrical Engineering Technology at Purdue. That is the school that is related, is talking to that company specifically. So just let you know, job market out here in the near future.
Or facility and founded. Forming a discipline structure with covalent bonds. That is, they share their electrons, so there are a total of 8 valence electron atoms, resembling bulk gases. The most stable elements known to humankind. If you don't like chemistry, don't think. The important thing here is to understand 8 electrons per atom is the magical amount that keeps everything tightly connected. In fact, they are so connected that when a neutron wants to go through silicon, the electrons that make it up cannot move, hindering the full current. However,
Ever see like silicon by itself is a good insulator? Makes sense.
it can be changed through a process known as doping, in which impurities are added to silicon to control its conductivity and turn it into an N-type or P-type semiconductor. If that impurities that have 5 valence electrons instead of 4, then we will have atoms with a total of 9 electrons. And since 8 was our magic number, we could say that one of the electrons will be left over or be freer than others, which will allow it, when connected to a power source, to move and act as a conductor. This alloy is known as N-type semiconductor because it has excess electrons, which, let's remember, have a negative charge. On the other hand, if we use the doping with impurities that have 3 valence electrons, we will have atoms with a total of 7 electrons. This means that we would have a gap, allowing electrons to move through it and generating the movement of the gaps in the opposite direction. Since this alloy would have 1 less electron in its stable form, it would have a positive charge, and it would be called a P-type semiconductor. Moreover, to simplify the visualization, we will say that each hole corresponds to a positive charge. This way, when a p-n junction is generated, depending on the polarization of the voltage source, there will be 2 possible results. If the positive pole is connected to the N-type semiconductor, and the negative pole is connected to the P-type semiconductor, the holes and free electrons will move away, preventing an electric current from being generated. This case is known as reverse polarization. On the other hand, if we reverse the polarity of the voltage source, the free electrons of the N-type semiconductor will be able to jump through the P-type semiconductor and close the circuit, allowing the passage of the current. This case is known as direct polarization, and it is precisely here that the physical phenomenon that produces the emission of light occurs. If we return to our visualization of the atomic structure, and we focus exactly on the point in which the 2 semiconductors make contact, we are going to find that electrons are being moved from an atom with more valence electrons to an atom with fewer valence electrons. This is extremely important because this difference in the amount of valence electrons is also related to the amount of energy that they possess. In other words, an electron that is in an atom with 5 valence electrons has more energy than another electron in an atom with 3 valence electrons. This means that every time an electron crosses this junction, there is energy see them shine continuously. There are two main reasons. The first one is that in many cases our eyes are unable to see the spectrum that is being emitted. I couldn't find an exact demonstration of this, but I did find a video in which the solar panel emits infrared light when applying a voltage, and a diode generates a voltage by being enlightened, all of which is related to the same phenomenon. The second reason why a common diode does not shine is simply the shape. If we think the light is being generated only at the points where the two semiconductors are in contact, how are we going to see them if for the most part this area is being covered? In this patent in which they describe one of the first light-emitting diodes, the solution is extremely simple: to move the semiconductors away from the connectors so that they do not cover the emitting light and reduce the thickness of one of them to such an extreme that light is able to pass through. In a way, we could say that this hasn't changed much to this day. Let's analyze an LED from the inside out. The first thing we will need is a substrate where we will put the rest of the materials. To this, we add a layer of N-type semiconductor and then another thinner P-type semiconductor layer. The order is important because the transformation of energy occurs when reaching the latter layer. Then we add some cable so that the electric current can flow between the semiconductors and the light is emitted, being extremely thin so it doesn't cover it. Technically, only with this we already have a functional LED. But to be more efficient, we will add a small reflector to direct the light, which will be integrated in one of the electrodes. And before covering everything in transparent epoxy resin, so that the set is more resistant, we will add one last element, a layer of phosphorus, although this is used only in some cases such as white light. In this particular case, the diode is actually emitting a blue light, which upon impact on the phosphorus layer causes this to emit a more yellow light. The mixture of these two spectra is what generates the perception of seeing a white light. The last thing I want to talk about is RGB diodes that can produce multiple colors. Although the truth is there is not much mystery left to it. The RGB
So that yellow stuff with the phosphorus. Okay, so you know how like they have different light bulbs, like they have cool, they have soft colors. That has to do with how much phosphorus they put in there. If they don't put much phosphorus, it comes out more blue, more like the daylight. Put more phosphorus, that becomes more warm, like, so there's that spectrum. That makes sense? Okay. The RGB, this is just like different colors of LEDs.
RGB name refers to the colors that compose it: red, green, and blue. Well, indeed, within this type of LEDs, there are 3 pairs of semiconductors specifically selected to produce each color, and by independently varying the voltage that passes through each of them, the perception of different colors is generated. I remind you that there are several more animations on my channel in case you want.
So, yep, worksheet due on Thursday.